What's up, everyone? Today's a big step forward. Everything we've covered so far has been building towards this, and now we're finally getting into something that's actually used in real zkSNARK systems. In this video, we're diving into the KZG Polynomial Commitment Scheme. It's a super cool polynomial commitment scheme and can be used to build a zkSNARK system, but also can be used in other applications as well, such as data availability sampling. As the name suggests, polynomial commitment schemes are all about committing to a polynomial, so you'll want a solid understanding of polynomials first. If you haven't seen my earlier video on that, I recommend watching it before continuing. Otherwise, this might get a bit confusing. There are also different types of polynomial commitment schemes, and KZG specifically is based on elliptic curve pairings. So if pairings aren't familiar yet, make sure to check out that video as well before this one. Once you're comfortable with those prerequisites, let's jump in and get started. Last time, I mentioned that polynomials are especially important because a SNARK can be thought of as a PIOP, a polynomial interactive oracle proof, combined with a PCS, a polynomial commitment scheme. We'll cover PIOPs later on, but today we're focusing squarely on the KZG PCS. So let's start by defining what a polynomial commitment scheme actually is. A PCS is a special kind of commitment scheme, which means we should first take one small step back and talk about commitment schemes in general. A commitment scheme is a protocol between two parties, a prover and a verifier. It allows the prover to commit to some piece of data in a way that they can't change later. Commitment schemes have two phases, the commit phase and the reveal, which is also called the open phase. During the commit phase, the prover takes their data, computes a commitment, and sends that commitment to the verifier. From that point on, the prover is locked in. They can't change the data anymore. Later, when the prover wants to reveal the data, they send an opening to the verifier, and the verifier checks that this opening matches the original commitment. If it matches, they accept. Otherwise, they reject. With that in mind, let's walk through a simple example. A standard cryptographic hash function, like SHA-256, can be used to build a commitment scheme that fits our definition. Suppose the prover has some message, say the string hello world, that they want to commit to. In the first phase, the commit phase, the prover computes SHA-256 of hello world, which equals B94D27, etc. This output, B94D27, is the commitment, and the prover sends it to the verifier. Later on, during the open phase, the prover reveals the message by sending the message itself, hello world, in plain text to the verifier. The verifier can then hash it themselves and check that SHA-256 of hello world really does equal B94D27, confirming that the opening matches the original commitment. If the prover tried to open the commitment with a different string, like sending the verifier jello world, the hash would not match B94D27, and the verifier would reject this. And in fact, any computationally bounded prover can't find any other string that hashes to that same value. That's exactly why this construction works as a commitment scheme. Once the prover sends the hash, they're locked in. They're committed to hello world, and they can't produce a different opening that would still convince the verifier. The property that we've been relying on so far, where the prover is locked into their original message and can't change it later, is called binding. Binding is a required property of all commitment schemes. Once you commit, you don't get to change your mind. There's also a second property called hiding. The definition of hiding is actually slightly tricky and subtle. Formally, how it's defined is that if someone gave the verifier two messages and the commitment to one of them, the verifier can't tell which of the messages was committed to before the commitment is opened. In our example, SHA-256 of the message is actually not hiding under this definition. If the verifier is given the two messages, hello world and jello world, and the commitment of B94D27, the verifier could hash both of these messages and immediately determine which one was committed to. So to be clear, hiding means that the commitment itself doesn't reveal which of these two messages was committed to. This is the standard definition of hiding. Later on, we'll actually relax the definition to a weaker definition of hiding, as presented by the KZG paper, because it's good enough for what we need for zkSNARKs. This weaker definition informally basically boils down to From just looking at the commitment, you can't figure out what the message was, even if the commitment leaks some information. Our SHA-256 based example fulfills this weaker definition of hiding. You'll often see words like computational or perfect placed in front of binding or hiding. For example, someone might say a scheme is computationally binding. This means the binding property holds against any adversary with a realistic, bounded amount of computation. Basically, what's feasible with today's computers in a reasonable amount of time. The same reasoning would be true if someone were to say a scheme is computationally hiding. One subtle point. This definition generally assumes classical computers. That is, the kind of computation we can actually do today. If someone had a large enough quantum computer, some computationally binding schemes could potentially be weakened, because quantum algorithms might give an advantage in breaking the binding property. So when we say computationally binding here, we mean security against classical, realistically bounded adversaries. In our example, using SHA-256 to build a commitment scheme is computationally binding. As we discussed earlier, a prover can't find a different string that hashes to the same value, like B94D27, within any reasonable amount of time using current technology. However, if a prover had unlimited time or unlimited computational power, a hash collision could be found. In that case, the prover could open the same commitment in two different ways and potentially fool the verifier. Therefore, it's not perfectly binding. Perfectly binding, on the other hand, means that even with unlimited time, unlimited computational power, or any future technology, it is fundamentally impossible for the prover to change their commitment. In practice, computationally binding commitment schemes are more than sufficient for our purposes. And as you might expect, the same distinctions apply to hiding. We can talk about schemes that are computationally hiding or perfectly hiding, depending on whether the hiding property holds against bounded or unbounded adversaries. With that out of the way, let's return to polynomial commitment schemes, or PCS for short. These are just a special type of commitment scheme. Instead of committing to some arbitrary data, like hello world, a PCS lets a prover commit to, you guessed it, a polynomial. Because they're a type of commitment scheme, PCSs are binding. Once the prover commits, they can't change their polynomial. So you might be thinking, what's so special about a PCS? Couldn't I just hash my polynomial using SHA-256 like we did before? Well, the cool part about PCSs is that they offer a lot more. They come with extra features that make them much more powerful and versatile than just using a simple hash. Some of the really cool features of the PCSs we'll be looking at are the following. They are computationally hiding, at least by the weaker definition we talked about, which means the verifier can't figure out what the polynomial is by looking at the commitment. They have private openings. Even in the open phase, the opening that the prover sends doesn't reveal the full polynomial. Instead, the verifier only sees the polynomial's value at a specific point of the verifier's choosing, along with a short proof, called an evaluation proof, that this value is correct. In contrast, in the SHA-256 example, during the open phase, the prover sends the original message, so the verifier learns everything during the open phase. They have compact commitments. The polynomial commitment itself is short, usually much smaller than the polynomial it represents. This is perfect for zkSNARKs, where succinctness is crucial. Remember that succinctness requires the proof size to be short, and the zkSNARK proof will include these polynomial commitments, so they need to be short. They have efficient verification. The verifier runs a fast algorithm to check that the opening matches the commitment. Quick verification is also necessary to fulfill succinctness, which ensures the zkSNARK proof can be verified efficiently. As I mentioned before, there are different types of PCSs, but the one we'll focus on today is called KZG, an elliptic curve pairing-based PCS. Let's dive in and see how it works. KZG stands for the three authors of the original paper that introduced this polynomial commitment scheme: Kate, Zaverucha, and Goldberg. Sometimes people also call it a Kate commitment for short. Earlier, we talked about commitment schemes having two phases, commit and open. For this particular scheme, though, we need one more phase at the very beginning, the setup phase, for this all to work. So now we have three phases: setup, commit, and open. The setup phase requires a trusted setup, meaning there's a trusted third party that performs the setup. Why trusted? Because the setup generates something called toxic waste. This is secret information that must be permanently deleted. If someone keeps it, they could forge proofs, and the security of the whole scheme would collapse. There are ways to reduce the trust in a single party, like splitting the setup across multiple participants, but that's outside the scope of this video. For now, we'll assume a single trusted party who properly deletes the toxic waste when they're done. So how does the setup phase work? Recall that in elliptic curve pairings, we have two groups, G1 and G2, and a target group, GT. We denote the pairing by E, which is a map from G1 and G2 to GT. Let's call the generator of G1 G, and the generator of G2 H. This is all public information, so the prover, verifier, and trusted party all know G, H, G1, G2, and GT. The trusted party picks a secret scalar S, which is the toxic waste. It's a scalar, not an elliptic curve point, and the security of the scheme relies on nobody else knowing it. Next, the trusted party computes a sequence of elliptic curve points, s to the power 0 times g, s to the power 1 times g, and so on up to s to the power d times g. Here, d is the maximum degree of the polynomial that can be committed to later on. If we want to make it possible for the prover to commit to a polynomial of degree d, we need all the powers up to s to the power d. The trusted party also computes s times h. Once this is done, the setup phase is complete, and the trusted party deletes s, ensuring the toxic waste is gone. Again, it's super important that this is deleted, since anyone that knows s could compromise the security of the PCS. In summary, the trusted party produces s to the power 0 sub 1, s to the power 1 sub 1, all the way up to s to the power d sub 1, and s sub 2. Here, the notation s to the power I sub 1 means s to the power I times g, and s sub 2 means s times h. The subscript 1 or 2 indicates which generator and therefore which group is used. Note that all of these are elliptic curve points, so the hardness of the discrete log problem ensures that given these elliptic curve points, nobody can figure out s or any of its powers. This set of points is safe to share with everyone, and that's exactly what happens. The set is called the CRS, Common Reference String, or more commonly known as the SRS, Structured Reference String. The key point is that the SRS is public. The prover and verifier know all these points, but neither of them knows S. Note that the setup phase can happen long before the commit or open phases, even before the prover has a polynomial to commit to. The only limitation is that the prover can only commit to polynomials of degree up to d, which is determined by how many powers of s the trusted party generated during the setup phase. Great. Now we move on to the commit phase. Let's say the prover wants to commit to a polynomial p of x, which equals a0 plus a1 times x plus a2 times x squared plus so on up to ad times x to the power d, where the a's are the coefficients of the polynomial. The prover takes each coefficient and multiplies it by the corresponding elliptic curve point in the SRS for G1. Concretely, they will take a0 and multiply it with s to the power 0 sub 1, and multiply a1 with s to the power 1 sub 1, and multiply a2 with s to the power 2 sub 1, and so on, and add all these terms together. So the final result will be a0 times s to the power 0 sub 1, plus a1 times s to the power 1 sub 1, plus a2 times s to the power 2 sub 1, plus, and so on, up to ad times s to the power d sub 1, which is an elliptic curve point in G1. Let's call this C. Pause for a moment and look at this. If we expand it using the definition of s to the power I sub 1 equals s to the power I times g, we get the following. Pause and notice what just happened. C is actually P of S encoded as an elliptic curve point in G1. We can write it as P of S sub 1 to make it extra clear. This is really cool because the prover doesn't know S, yet what they've done is that they've effectively evaluated the polynomial at the point S and pushed that value into a single elliptic curve point C, which is in group G1. And thanks to the hardness of the discrete log problem, even knowing C and G, nobody can figure out P of S or recover the coefficients of the polynomial. This point C is the polynomial commitment, which is why we denote it as C, and it's sent to the verifier. The beauty of this is that the polynomial could have a very large degree, many coefficients, but the commitment is just one elliptic curve point. This makes communication extremely efficient while keeping the commitment secure. Now we move on to the open phase. This is where the verifier asks the prover to open the committed polynomial at a point of the verifier's choosing. Concretely, the verifier picks some scalar z and asks the prover to reveal the value of the polynomial at that point. So the prover sends over a value y, which they claim is the value of p of z. Of course, the prover could just send over some random value y. How does the verifier know the prover isn't lying? How can the verifier be confident that this y really does equal p of z, where p is the polynomial the prover originally committed to? So in an opening, the prover doesn't only send the value y. They also send an evaluation proof, usually denoted pi, that allows the verifier to check that y is indeed equal to p of z. To understand what this proof is and why it works, we need one key fact about polynomials. Here's the idea. Recall a basic result from algebra, which was discussed in the polynomials video. If a polynomial evaluates to 0 at some point t, then it must be divisible by x minus t. For example, the polynomial x squared minus 4 evaluates to 0 at x equals 2, so it's divisible by x minus 2. In fact, x squared minus 4 divided by x minus 2 equals x plus 2. We can push this idea one step further. Suppose a polynomial p of x evaluates to some value y at a point z. That statement, p of z equals y, is equivalent to saying that the polynomial p of x minus y evaluates to 0 at z. We're not doing anything fancy here. We're just subtracting y from both sides. And now we're back to our previous case. Since p of x minus y equals 0 at x equals z, it must be divisible by x minus z. Let's do a quick example to make this concrete. Let's take p of x equals x squared minus 4 again, and evaluate it at z equals 3. We get p of 3 equals 5. That means the polynomial x squared minus 4 minus 5 evaluates to 0 at x equals 3, and therefore it's divisible by x minus 3. You can see that x squared minus 4 minus 5 divided by x minus 3 equals x plus 3. So in general, whenever p of z equals y, the polynomial p of x minus y is divisible by x minus z. Another way of saying that is that dividing p of x minus y by x minus z gives us a polynomial, not just a rational expression. Let's call this resulting polynomial q of x. This simple fact is the key idea behind how KZG openings work, and it's exactly what the evaluation proof pi is going to capture. If you want, feel free to pause the video here and convince yourself that this is really true before we move on. So let's return to the question. What exactly is the proof pi that the prover sends? The construction is going to look very similar to how the original commitment C was formed. The prover first evaluates the original polynomial p of x at the verifier's chosen point z, so they compute p of z equals y, and uses this y to compute p of x minus y divided by x minus z, which we said we were calling q of x. Assuming they did this properly, q of x will be a polynomial, like we said before. So q of x will look like b0 plus b1 times x plus b2 times x squared, and so on. Next, the prover uses the SRS in the same way that they used it to create c from p of x, but now instead they use the polynomial q of x. They take b0 and multiply it by s to the power 0 sub 1, and then b1 and multiply it by s to the power 1 sub 1, and b2 and multiply it by s to the power 2 sub 1, and so on. And then they add all of these points together. The result is the evaluation proof pi, which is an elliptic curve point in group G1. To see what this really represents, let's expand it out. We can see that pi is actually equal to q of s times g. We can write it as q of s sub 1 to make it extra clear. This is really cool because again, the prover doesn't know S, yet they've effectively evaluated Q of X at the point S and pushed that value into a single elliptic curve point, pi, which will serve as the evaluation proof. And thanks to the hardness of the discrete log problem, given only pi and g, no one can recover the value of Q of S itself. So let's recap. The prover first sends C, which encodes the polynomial P of X at the point S. The verifier then chooses a point Z and asks the prover to open the polynomial there. In response, the prover sends back the claimed value Y, which should equal P of Z, along with the evaluation proof pi, which encodes the polynomial Q of X at the point S. Both C and pi are elliptic curve points in group G1. Now we're ready for the final step, the verification algorithm. How does the verifier check that the prover isn't lying? Let me start by writing down the verification algorithm, and then we'll unpack why it works. The verification algorithm is an elliptic curve pairing check that checks whether E of C minus Y sub 1, comma, H equals E of pi, comma, S minus Z sub 2. Here, E is the pairing. If this equation holds, the verifier accepts and therefore believes the prover that the Y that they sent over is indeed P of Z. If not, they reject. So why does this work? What's actually going on here? We've already established that if the prover is telling the truth and that P of Z really equals Y, then the following polynomial identity holds. P of X minus Y divided by X minus Z equals Q of X. If we move the denominator to the other side, this becomes P of X minus Y equals Q of X times X minus Z. So at a high level, the verifier's job is to check that this equation is true. But checking equality of two polynomials directly would be expensive. This is where a key idea comes in. Recall the Schwartz-Zippel lemma that we covered previously. Instead of checking a polynomial identity everywhere, it's enough to check that it holds at a single randomly chosen point, since the probability of error will be small. In KZG, that random point is the secret value S from the trusted setup. So by Schwartz-Zippel, the verifier now is trying to check P of S minus Y equals Q of S times S minus Z. But the verifier doesn't have S. No one does, since it was deleted as toxic waste. Let's see what they have instead. They received C, which equals P of S times G, pi, which equals Q of S times G, and Y from the prover. The verifier chose Z themselves, so they have that, and they also have access to the generators G and H along with the SRS from the setup phase. Let's first see what would happen if the verifier instead checked the equation by multiplying both sides by G. The left-hand side of the equation now looks like P of S minus Y times G, which we can expand out to P of S times G minus Y times G, or in other words, C minus Y sub 1. So the left-hand side is straightforward, as the verifier has all it needs to compute this quantity, since it has C, Y, and G. The right-hand side is trickier. We now have Q of S times S minus Z times G. The verifier has pi, which is Q of S times G, but they don't know the secret value S, and for security reasons they never should. So they can't directly form the scalar S minus Z. So what do we do now? This is exactly where pairings come in. Recall from the pairings video that one of their key uses is to help us reason about multiplication in settings where we can't directly multiply elliptic curve points together. Let's modify the equation slightly by putting the bilinear pairing on both sides. Recall that a pairing takes 1 point from G1 and 1 from G2 as input. So the left-hand side of the equation looks like E of C minus Y sub 1, comma H, and the right-hand side now looks like E of Q of S times S minus Z times G, comma H, where H is the generator of G2. Now for the right-hand side, we can use the property of bilinearity to move the scalar multiplication across the pairing. So E of Q of S times S minus Z times G, comma H, equals E of Q of S times G, comma, S minus Z times H. And we can expand out S minus Z times H. So now we have E of Q of S times G, comma, S times H minus Z times H. At this point, the key question is, can the verifier compute all of this? And the answer is yes. Even though the verifier does not know S, they do have S times H from the SRS. And since they chose Z themselves, they can easily compute z times h. So they can form s times h minus z times h, which is also written as s minus z sub 2, without ever learning s. And of course, like we already stated, they have pi from the prover, which is q of s times g. Great. How about the left-hand side? We already said that the verifier can compute c minus y sub 1 with what it has, so it can easily compute the pairing e of c minus y sub 1, comma h. So the verifier really does have everything needed to perform the check e of c minus y sub 1, comma h equals e of pi, comma s minus z sub 2. So to take a step back and summarize, what that equation really is just using elliptic curve points and pairings to check the equation p of s minus y equals q of s times s minus z. And by Schwarzschild, if this is true, then with overwhelming probability, the polynomial identity p of x minus y equals q of x times x minus z is true. And if this is true, then the prover really did provide the correct value, p of z equals y. Let's summarize what we have learned. The KZG PCS has 3 phases: setup, commit, and open. During the setup phase, the trusted party chooses a random S, creates the SRS, and then deletes S. During the commit phase, the prover takes their polynomial p of x, and using the SRS, creates the commitment C and sends it to the verifier. The verifier then queries the prover at a point z of their choosing. During the open phase, the prover computes p of z, which we call y, and the quotient polynomial q of x, and uses the SRS to create the evaluation proof pi. They send y and pi over to the verifier. The verifier then checks if e of c minus y sub 1, comma h equals e of pi, comma s minus z sub 2, and accepts if it does, and rejects otherwise. And that's the magic of KZG. We've built a polynomial commitment scheme where the commitment is short, the verifier can get the value y equals p of z for any point z that they want. The verification algorithm boils down to a single pairing check, so it's fast. The verifier doesn't learn the original polynomial p of x. That's pretty awesome. So how is this useful? Well, in a SNARK or zkSNARK, we're going to need the ability for the prover to commit to a polynomial and not be able to change it later. Then we will need for the verifier to be able to obtain the evaluation of this polynomial at a certain point. KZG, as well as other PCSs, given their properties, will fulfill this exact role. Purely for the sake of time, I'm going to wrap up the technical part here, but I want to leave you with a few final thoughts. First, what we covered is the basic KZG scheme, where the verifier asks for an opening at a single point z. There's a straightforward extension to multi-point openings, that is, opening p of x at many points of the verifier's choosing, z1, z2, all the way up to zn, using the same single commitment c and a single proof pi. Of course, the prover would still need to provide all the claimed values, y1, y2, all the way up to yn. Second, the KZG scheme, as I've been describing, is not perfectly hiding, but can be made perfectly hiding by adding some randomness and making minor modifications to the commitment. Third, KZG in the form as I have described is interactive, because the verifier picks z and asks for an opening. But it can easily be made non-interactive using the Fiat-Shamir transform, turning the verifier's challenge into a hash of the transcript, as we have covered in the Fiat-Shamir video. Fourth, KZG is additively homomorphic, a neat property that some other PCSs we may see in future videos do not have. If you recall from a previous video, this means that if you take the commitments to 2 polynomials and add them, you get a commitment that is equivalent to committing to the sum of those 2 polynomials. Finally, KZG is elliptic curve pairing based, which means its security rests on the hardness of the discrete logarithm problem. If a quantum computer ever breaks discrete logs, this scheme would no longer be secure. That's it for now. Today we covered commitment schemes and the KZG polynomial commitment scheme. We started by defining what a commitment scheme is and the key properties it should have, binding as well as hiding, as well as the meaning of computational and perfect. Next, we introduced polynomial commitment schemes, or PCSs, and what makes them useful. Then we dove into the intuition and the math behind one specific PCS, KZG, which is based on elliptic curve pairings. I hope you enjoyed this deep dive and keep following along in this series. See you next time.